Hello guys, I hope you're good. I'm also fine. So anyway, today we'll be wrapping up differentiation. So we're going to discuss application of partial differentiation. So let's start with small changes and the formula that we always use when we're calculating small changes. So you'll be given, so if z is a function of x and y, then our small change in z is going to be equivalent to partial derivative of z with respect to x multiplied by small change in x plus partial derivative of z with respect to y multiplied by the small change in y. So this denotes small change in z, and then this denotes small change in x, this denotes small change in y. So how are we going to know that we are calculating small changes when we're given our question? You'll just see the weight. The question will just tell you calculate approximate change. I'm quite sure it will say that they have to tell you that calculate approximate change. So that's how you're going to know that you are calculating small change. So you have to use this formula, but of course you will have to manipulate this formula with the use of what you are given. You cannot be always be given that function. You cannot be always be given that z is a function of x and y. So you can't always write your formula like this. You have to manipulate it in a way that it applies to the equation that is given to you. So you'll see how what I'm saying with regards to the question that we're just gonna do now. So I'm just gonna do an example and explain this thing. So yeah, let's start with this example. All right, we're given that the current flowing in an electric circuit is given by Ohm's law, I equals to V over R amperes. Calculate the approximate change. You see, calculate the approximate change. That's how you know that you're calculating small changes. So you need to use this formula. And then in the current, if the voltage decreases from 120 volts to 118 volts, and the resistance increases from 200 ohms to 200.04 ohms. So you're also given small changes. You can see that they're saying resistance increases from 200 to 0.04. So it increased. I mean, like, your resistance increased by 0.04 from 200 to 200.04. That means your small change in R is 0.04, and then they say the voltage decreased from 120 to 118 volts. So that means your small change in V is -2 volts, right? So yeah, let's start. So we can see that we can always start by differentiating, like differentiating partial with respect to the other variable, and then also with respect to the other variable, so that we can just substitute in our formula. You'll see what I mean just now. So what I'm saying is this: we can always start by saying that partial derivative of I with respect to V is equivalent to it. So we're going to differentiate this equation with respect to V. So that means R is a constant. So when we differentiate with respect to V, we're just gonna get 1 over R. And then we also differentiate with respect to the other variable, that means partial derivative of I with respect to R is then going to be equivalent to what? Minus V over R squared, right? And then how about our small changes? So let's now write our small changes. So small change in V is equivalent to what? Small change in V. So they say the voltage decreases from 120 to 118 volts. That means the small change is negative. As long as it decreases, you have to always put it as negative. So that's going to be -2. And then how about the small change in R? So small change in R is going to be equivalent to what? They say the resistance increases from 200 to 200.04. That means our small change is just 0.04. And then that's it. So now we just need to rewrite our small change our small change formula with respect to this formula. So let's do that just now. So that means our small change in I is going to be equivalent to partial derivative of I with respect to V multiplied by the small change of V. Also, another thing that so that they avoid memorizing and having to stress about memorizing this. So you'll always, whenever you're differentiating with respect to a variable, that variable you have to multiply by that small change of that variable. For example, here I was differentiating I with respect to V. I must multiply by small change in V. And then now when I say plus partial derivative of I with respect to R, then I must multiply by what? By small change in R. So yeah, that's how to best memorize these things. They are not that bad. So now we can just substitute. We have all our we have everything that we need there. So our small change in I is going to be equivalent to what we already found, partial derivative of I with respect to V, which is this one. So we're just gonna substitute 1 over R multiplied by small change in V is going to be -2 plus, oh so let's not substitute this small change. We'll substitute everything when it's time. Let's not rush. So let's not rush so that I explain step by step. All right, so now let's substitute our partial derivative of I, which is just -V over R squared, -V over R squared, and then multiplied by small change in R. Okay, now we can see that we have value of R, V, R squared, but we didn't discuss how much are the magnitude of V and R. So cram this or memorize the following that I'm going to say. So the values of these variables is or what are the ones that you get initially before the changes. For example, voltage here, they said it decreases from 120. So that means this 120, it is the initial state of the voltage. So that's the number that you always put here in these variables. So if it's voltage, that means you'll take the initial state of voltage, which is going to be 120, and then the initial state of resistance, they said it's 200. So that means you're going to take 200 as your R. So yeah, let's substitute. So partial derivative, no, small change in I is then going to be equivalent to 1 over R. We say this 200 multiplied by small change in V. Small change in V is going to be what? -2. We've already discussed that, and then plus our V, we said our V is going to be 120. So this is going to be -120 divided by what? Our R squared, which is just 200 squared. 200 squared multiplied by change in R. So our change in resistance, we have already discussed it, that is 0.04. And then you just press on a calculator to get your small change there. So your small change is going to be approximately equals to what? To, when you press a calculator, you should get something like -0.0102, right? 1012, I mean amperes. So this is going to be the answer for this question. So yeah, that's it, guys. I hope it makes sense, right? I hope it makes sense. And then let's see if we can do other questions. So let's now discuss percentage change, because it also, there are also questions for percentage change. So percentage is also very easy, because on percentage change you will be told that there is this calculate the approximate percentage change. So it's also easy like that. Like, these things are easy, guys. So whenever you are told that you should calculate the approximate percentage change, then that means now you're calculating percentage change, and then the formula is almost similar. It's similar to that one of percentage change of small change, basically. So now let's start with the formula, then I explain how to manipulate these things. So for percentage change, it is the same thing that if z is a function of x and y, so we will again use that as an example. If z is a function of x and y, then our percentage can be calculated as follows. So percentage change of z, is going to be equivalent to what? Partial derivative of z with respect to x multiplied by what? By this percentage change in x, plus partial derivative of z with respect to y multiplied by the small change in y. So this is going to be the percentage change in x, and then this is going to be the percentage change in y, and then then this is going to be the total approximate percentage change of z. So you'll be told that x changes with this percentage, and then y also changes with respect to this percentage, so you just substitute there. And then after that, so the only thing that makes percentage change to be different to a small change is that we are going to take out z as the subject of the formula. So after you have differentiated z with respect to z, with respect to y and x, you'll realize that you can be able to take z as the subject of the formula, and then you'll see the change after that. So well, don't be confused. I'm gonna do an example to explain what is really going on here. So it's very easy. So stay tuned. It's not confusing. Okay, we have an example here. This is the example that we're going to discuss with regards to percentage change. So we're being told that the modulus of rigidity of a metal bar is given by G equals to R to the power 4 multiplied by theta divided by L, where L is the length of the bar, and R is the radius, and theta it's the angle of twist, and then we should determine the approximate change. Like I've said, guys, for you to know that you're calculating percentage change, they will tell you that calculate the approximate percentage change. So that's how to know what are you doing. that's how to know what you're doing. So determine the approximate percentage change in G when R is increased by 2% and theta is increased by 3% and L is increased by 2%. So another thing, they will tell you that this is increased by this percentage. Or whenever you're seeing percentage increases, you know that also this is a percentage change. We are calculating percentage change. So here what we are being told that the percentage of that is that, and the percentage of that is that. So let's start, and then I explain what is going on, because you need to know, man. So let's go. So so I should calculate the percentage change in G, right? So let's first I prefer differentiating with respect to all of those variables first that they have changes before I write my formula down, so that when I write my formula down, I just substitute. So let's work like that as well. So we're going to differentiate G with respect to R, and then later with respect to theta, and later with respect to L, and then we write their changes down, and then we write the formula of percentage change, and then we substitute all of those things. It's always easier like that. Okay, let's go. So partial derivative of G. So partial derivative of G with respect to R. Partial derivative of G with respect to R is going to be what? This is going to be, so we're differentiating this g with respect to r. That means theta and L are constants. So this is going to be 4r cubed, right? This is going to be 4r cubed theta divided by L, right? Yeah. And then now let's calculate the partial derivative of g with respect to what? To theta. Now how much is this going to be? That means r and L are constants. So with respect to theta, we're just gonna get r to the power 4 over L, r to the power 4 over L. And then how about partial? So last one, partial derivative of g with respect to what? With respect to L. With respect to L. So that means now r and theta are constant. So if we take L up there and then it becomes L to the power negative 1, then we differentiate, you will see that we'll end up getting negative r to the power of 4 theta divided by L squared, just like that. So now let's write the small changes of these things. So small change of r is going to be equivalent to what? They told us that r is increased by 2%. So small change in r is going to be 0,02r. So I'm gonna write 0,02 r. So they said r is increased by 0,02. So r is increased by 2%. This is the one. And then now let's write the small change in theta. So small change in theta is going to be equivalent to what? They told that theta is decreased. So when they say decreased, we have to write it as negative. So this is going to be negative 0,03%. And then the last one, small change in L. They said L is increased, so this one is positive. So small change in L is going to be 0,02 L, just like that. And then now we can rewrite our formula, right? So now our small change in G, our percentage change. So our percentage change in G, is then going to be equivalent to the partial derivative of G with respect to R. Remember guys, whenever we write the one with respect to R, that means we must multiply by small change in what? Oh, percentage change in R for this case, and then plus, and then when we write the other one, partial derivative of G with respect to theta, that means we must multiply by what? By small change, percentage change, I mean, in what? In theta. And then plus what? Plus the last one, partial derivative of G with respect to L. We are going to multiply by percentage change in L. So always guys, if you wrote the formula of partial derivative of G with respect to R, that means you should multiply with respect to with the percentage change in R. If you differentiate with respect to theta, you should multiply with percentage change in theta, and like that and like that. So that's how the formula goes. So yeah, don't be confused. So yeah, let's go. Now we have everything. We're just gonna substitute there, and then we see what is going on. All right. So small change in G. So small change in G. So small change in G is going to be equivalent to what? We're just gonna substitute partial derivative of G with respect to R. We've already calculated it, so we're just gonna substitute it here. How much are we going to get? Well, we're just gonna substitute. So R cube theta divided by L. So this is how it's going to be, and then you multiply it by percentage change, which is going to be 0,02 R, and then we say plus. Now you put G with respect to theta, that's going to be R to the power 4 over L. So we substitute R to the power of 4 upon L, and then we multiply by the small change. So the small change here, I wanted to write theta. Sorry, I don't know why I wrote that thing. Am I crazy? Yes, I think I am. So yeah, we multiply by negative 0, 0.03 theta plus what? Plus this one that we have here, percentage partial derivative of g with respect to L. So I'm just going to substitute it here, and then this is going to give me negative r to the power 4 theta divided by L squared, multiplied by what? Multiplied by the small change, percentage change is going to be 0, 0.02 L, just like that. Now you have this equation. So from here, I think I've already told you that we have to make, so if it was z, if we were given a function of z with respect to x and y, then at the end of the day, we're supposed to make z the separate of the formula after substituting everything. So that's what, this is how we're going to do it. So remember, g equals to this guy, right? So we should make sure that we end up having g. So okay, well, look at this, guys. So when we multiply this and that, we're going to get r to the power of 4 theta L, and then 4, of course, there's a constant or is a coefficient. So let's rewrite this like this so that you don't get confused. So this is the same as 4r to the power of 4 theta divided by L. Okay, I just multiplied this r multiply. I made r to multiply that, so it added with that one to get that. So here that means I'm just left with 0, 0.02, and then plus I do the same here. I multiply theta with that guy. I end up getting that r to the power of 4 theta divided by L, and then negative 0, 0.03. It's what is left after multiplying the theta with that thing, and then plus, now I multiply L with this thing, so 1 L will chop 1 L there. We'll just be left with negative r to the power of 4 theta divided by L multiplied by 0, 0.02, just like that. So you can see that we have r to the power 4 theta L, r to the power 4 theta L, r to the power 4 theta L. So we can take it out as a common factor there. That means our percentage change in G is now going to be r to the power of 4 theta divided by L multiplied by what? Multiplied by 4 into 0, 0.02. So for this case, after we have taken out r to the power 4 theta divided by L, we will be left with 4 by that. And then here, when we take out that as a common factor, we'll just be left with negative 0, 0.03. And then we take out this as a common factor, we'll be left with negative that. So negative 0, 0.02. Just like that. And then remember, guys, that r to the power 4 multiplied by theta divided by L is equivalent to what? To G. So we're just gonna substitute there and then say percentage change in G is this is G, right? We've just agreed that we're told that this is G, and then multiplied by what? You use your calculator to press what is inside here. You will get something like 0, 0.03. So 0, 0.03 is what you're going to get inside the brackets there. So what does this mean? Then this means that remember, this isn't, if you this isn't percent, so if you convert this to percentage, you'll get that this means that G is increased by 3%. So there is an increase of 3%. Yeah, so therefore you can conclude now that there is an increase of 3%. So you will just convert this to percentage and then you'll get 3%. So then you conclude, so that's 3%. So the difference between small change and percentage change is that on percentage change we end up taking the formula that we're given and make it the subset of the formula. Like you see how we made G as a common factor here, like that's the difference between small change and percentage change. Also another thing, that for percentage change you'll be given things in percentage, and then meanwhile on small change you're not given things in percentage. Also you're not told to calculate percentage change in small change. So that's the difference. So always remember that for percentage change you must always make the formula that you are given, like you'll have to take it as a common factor and then substitute there. Also it makes sense that you don't know what R was before, so there was no way that you were going to substitute the value of R here. You did not know what initial R was before. They just told you it increased by that, so you were only given the small change. You were not given the values of R, theta and L, so there was no way that you're going to substitute. So that's another difference between small change and percentage change. So yeah, that was it for that one. Now let's quickly see if we can discuss. Okay, now let's discuss maximum percentage change. So this one is also very easy. So they will tell you in the question that calculate the maximum percentage change. So they will always tell you to calculate maximum percentage change. So how do we then do it? So well, it's easy. Let's discuss it. So I'll start with the formula for this maximum percentage change. So it is the same thing. So this formula is the same as that on small change and percentage change. So let me write it down. So if z is a function, of x and y, then what? Then the maximum percentage change in z, is going to be equivalent to the partial derivative of z with respect to x multiplied by the percentage change in x, plus partial derivative of z with respect to y multiplied by small change in y. So here partial derivative of z denotes the maximum percentage change in z. Meanwhile this denotes small change, this denotes the percentage change in x, and then that one denotes the percentage change in what? In y. So yeah, this is the formula that we're going to use. Then another thing, or the only special thing about maximum percentage change is the following. So memorize what I'm going to say. It is that you will be given the change in plus minus. So you'll be told that x changes by a percentage of plus minus 3, and then y changes by plus minus 4, for example. So that means from that information, after you have differentiated and wrote down the formula, you must make sure that you take the sign of this change so that it makes your equation, this equation, positive. You understand? So if you have negative this, that means this one you must also take it as a negative, so that the negative and the negative, they multiply each other to get a positive. So if it's positive, then you take them as positive, so that you end up getting a positive answer. That's why it's called maximum percentage change. Unlike in percentage change that we just discussed previously here, we were just taking, if it's decreased, then we're going to take it as negative. If it's increased, then we're taking it as positive. So percentage change, you won't be told that it's increased. You'll be told that it changes by plus minus certain percentage, so that you just need to manipulate and make sure that you take the sign that will make that equation positive, because we are solving for the maximum percentage change. So I hope that makes sense. So yeah, let's go. Let's see if we can do one example and then see how that applies to these things. So here's one example. Okay, we're going to solve this and apply all the information that I was trying to preach there. I was busy preaching about. Okay, so here's the question. It says that research shows that the resistance R of a blood vessel of length L and radius R is R equals to KL squared divided by root of R, where K is a constant. So they're telling you that K is a constant. The application of certain drug has the effect of changing the radius of the artery by plus minus 1.5% and the length of the artery by plus minus 0.75%. Find the maximum percentage change in resistance R. So we are going to calculate the maximum percentage change. So you see, the question will tell you calculate the maximum percentage change. So that's how you know that you're calculating for the maximum percentage change. And what you should remember is that you have to take for the signs of the changes, that the percentage changes, you have to take the sign. Since you are given positive, minus, you must take the one that will end up giving you a positive sign. And then also on the other one, on everything. So let's go. So let's go. Let's do this one. So like always, I prefer to first calculate these things like this. So first write down the partial derivative of that. So since here this one's a constant, we cannot differentiate with respect to it. We're going to differentiate only with respect to L and R, also because of we're only given the percentage change of what is this, of R, as well as for the length. So they also told us that K is a constant, so we can't differentiate with respect to it. We're only going to differentiate with respect to L and R. So yeah, let's go. So partial derivative of R. So partial derivative of R with respect to what? So let's start with the L one. So partial derivative of R with respect to L is going to be equivalent to what? With respect to L is going to be equivalent to, so we're differentiating with respect to L, meaning that R and K are constants. So this is going to be 2KL, right? So this is going to be 2KL divided by a root of R. And then how about with respect to R, small r? So partial derivative of R with respect to R is going to be equivalent. So that means we're going to treat K and L as constants, and then we differentiate with respect to R. So the best way to do this is just to take R up there so that it becomes R to the power -1/2. Then you differentiate from there. You will see that you will get something like negative KL squared divided by what? By 2R to the power of 3/2. Yeah. And then now let's discuss the, okay, let's just write down the small changes. So the small changes, the percentage change. So now let's write the percentage change in L. So the percentage change in L is going to be equals to what? They say the length of the artery increases by plus minus. So this is plus minus 0.75, so we can write it down as 0.0075. I'm just converting it from percentage, so 0,0075 L, right? So multiplied by L, just like that. And then how about this percentage change in R? So percentage change in R is what? It's plus minus that. So plus minus that, that's your 0. Yeah, 0. That's your plus minus 0,015 R. So now let's write down the formula of percentage change in R with respect to this equation. So that means that our maximum percentage change in R is equivalent to what? It is equivalent to partial derivative of R with respect to L multiplied by small change in L plus partial derivative of R with respect to R multiplied by small change in R. So yeah, this is how it's going to be. Then from here, we're just going to substitute our percentage change in R because we've already calculated it, we've already calculated that, and then we just substitute, and then we manipulate these signs with regards to making it positive, making this equation positive. So yeah, now let's start. So partial derivative of R is going to be equivalent to, so we're just going to substitute this, which is 2KL. So it's going to be 2KL divided by root of R, like that. So because of this one, this is positive, like it's a positive. So for us to get a positive, we just want positive signs here. So now we must substitute our small change in L. That means we must take the positive one so that we get a positive value when we multiply these two. So that means we're going to substitute our small change in L as positive 0,000075 L, just like that. And then we close, we say plus. Now we copy the other one. So the other one of partial derivative of R with respect to small r is going to be equivalent to negative k L squared divided by 2r to the power 3 over 2, just like this. And then we multiply by small change in or percentage change in R, I mean. So that's going to be so because of, you see this negative here, this negative, so we must take a sign from this small change in R that will make the multiplication of this and that positive. So since this one is negative, that means we must take the small change as the percentage change as negative. So that means we're going to take that one as negative 0,015 R. So yeah, that's how to manipulate percentage change. And then from here we just need to multiply, then take R as this common factor, and then we'll see what is the maximum percentage change. So I'm going to multiply L by that, and then multiply R by that, and then you'll see what we are going to get. So maximum percentage change in R is equivalent to what? To, when I multiply that, I get 2k L squared divided by root of R. So what I did here, I just multiplied this L by that, so then I got L squared multiplied by 0,0075, and then plus. So here I'm going to multiply R by that, and then that's going to be how much? That's going to be k L squared divided by 2r to the power 3 over 2. 3 over 2, just like that. That's the exponent. And then 0, 0.015. Oh, no. This is not going to be 3 over 2 because of we are going to, when we multiply r by this, so since r is an exponent of 1, then 1r will get subtracted there, and then we'll only be left with r to the power 1 half over r to the power half. So this r to the power half is the same as root of r. And then another thing that I did there, I multiplied this negative and that negative to form a positive. So yeah, from here from here, since r equals to kl squared divided by root r, we are going to do this. We are going to take out kl squared over root of r as our common factor, kl squared over root r as our common factor. So let's do that. So this is going to be maximum percentage change in r. We take kl squared r, l squared over root of r as our common factor. We will be left with 2, these 2 here, multiplied by that, multiplied by 0.0075 plus what? Plus so after taking out kl squared divided by root r, we'll be left with 1 over 2. For this case, 1 over 2 multiplied by 0.015, and then we close. So we know that kl squared over root r is equivalent to what? Kl squared over root r is equivalent to r. So percentage change in r is r multiplied by what? So you're going to use your calculator to press this, and then you will see that you will get something like 0.00 0.0225, sorry, 225, just like that. And then this then means that there is our maximum percentage change in resistance is 2.25%. So this is the same as small change in r is what? R multiplied by 2.25, right? Percent. So this is going to be our maximum percentage change in r. So r is going to change by the maximum percentage of what? 2.25%. So that's what that means. So yeah, let's see if we can discuss something else. So yeah, rate of change is also very easy. So let's now discuss rate of change and how to go about it. So let's go. So now let's start with the formula, guys. Let's start with the formula. First thing first, let it be the formula. So okay. So this is the same thing. I'm again going to use if you're given that z, it's a function of x and y. So then your formula for rate of change is going to be this. So it will be the z dt is going to be equivalent to partial derivative of z with respect to x multiplied by the x dt, right? And then plus partial derivative of z with respect to y multiplied by the y dt, just like that, multiplied by dy dt. And then from here we are going to just substitute. So you'll be given a certain equation. It could be a z as a function of x and y. Then the rate of change in z is going to be given by this formula, and then you just substitute. So how will you know that you are now calculating rate of change? You will be told that x increases at a rate of 2.3 second 2 meters what second, you'll be told, and then y decreases by 5 units per second, for example. So you'll be told things like that. So that's how you know that you are using you should calculate the rate of change. And then the formula that you use has to be this one. Of course, you need to manipulate it with regards to the formula that you are given. Also, you will be told that calculate the rate of change. So it will be clear in the exam questions or in the questions that you'll be trying to solve that what are you solving for, and then you'll solve after that. So now let's just use an example to explain this theory, and then we solve just like that. So let's go. Let me take one example here, and then we solve it. Okay. Okay, here's going to be our first example. They say find the rate of change in y if y equals to L divided by 1 plus e to the power negative x. So you're told that you should find the rate of change. So you should know that you should manipulate your formula, and then it end up looking like that, and then you just substitute. Yeah, so let's go. We should find the rate of change. So in y, so if y is given as L divided by 1 plus e to the power negative x, the instance x equals to 2. So we are told that x equals to 2 and L equals to 100. If L increases at a rate of 5 units per second and x decreases at a rate of 3 units per second, so we should find the rate of change. So let's go. Like always, I prefer writing the derivatives or the partial derivatives first, and then I'll just substitute them into the formula after writing down the formula. So instead of just putting everything into the formula same time, I prefer differentiating separately, and then I'll substitute just into the equation after. So let's work like that. Let's continue with that format. It helps in terms of avoiding mistakes. So partial derivative of y. So partial derivative of y with respect to what? With respect to L. So let's start with L first. So let's start with partial derivative of y with respect to L. So when we differentiate with respect to L, we will just get 1. We will just get 1 over 1 plus e to the power negative of x. So that's going to be our partial derivative of y with respect to that. And then with respect to x, so partial derivative of y with respect to x will be equivalent to what? So if we differentiate with respect to x, that means L is a constant. So to do this nicely, we can take this denominator up there, and then we make it to have exponent of -1, right? So if we do that, then you'll get something like okay, let me write it here. So if we write that y is equivalent to L multiplied by 1 plus e to the power negative x to the power of negative 1. Then L is a constant, right? When if we are differentiating with respect to x. So there's going to be negative 1 by L, and then this bracket to the power negative 2 multiplied by e to the power negative x multiplied by negative 1. Yo. Okay, let's write it. Let me write it. It's down so that you understand. So partial derivative of y with respect to L for this case will just be negative L because of this negative here. This negative will multiply L there, and then we'll take this. This is going to be 1 plus e to the power negative x all to the power of negative 2. Then you substitute negative 1 there from negative 1. And then you multiply by the derivative of what's inside there. So you multiply by the derivative of what's inside. So the derivative of 1 is 0. Derivative e to the power negative x. It becomes negative e to the power negative x, just like that. And then you multiply this term and that term, you will get positive. You will get positive e to the power of x. You will get positive e to the power of x multiplied by L. So you'll get L multiplied by e to the power negative of x divided by what? Divided by 1 plus e to the power negative of x squared. So another thing that I did there was just to take this one down and have a positive exponent. So that's how I was explaining how to differentiate that one. So yeah, let's go. And then the rates, you're also given the rates. So you're given that the what, the y, the L, the y, the t, I mean the L, the t. You're given that the L, the t, the L, the t is equivalent to what? You're told that L increases at a rate of 5 units per second. So the rate is 5. And then here, how about x? So the x, the t is equivalent to what? So the x, the t, you're told that x decreases. So it decreases, that means it's negative. So that's going to be negative 3. So now we can rewrite our formula. So the what? The y, the y, the t, the y, the t, the y, the t, the y, the t is going to be equivalent to partial derivative of y, partial derivative of y with respect to L multiplied by dl dt plus partial derivative of y with respect to x multiplied by dx dt, just like that. And then we're just gonna substitute from here. So partial derivative, dy dt, I mean dy dt is then going to be equivalent to what? So we're just gonna substitute our formulas. We already have 1 divided by 1 plus e to the power negative x multiplied by, we can leave this in the L dt for now, the L dt, and then plus this other one we calculated and found L multiplied by e to the power negative of x divided by 1 plus e to the power negative of x squared, like that, and then multiplied by dx dt. Then you are given the value of x, they give the value of L. We also have our rates, so we just need to substitute here and then get our rate. So let's go. X equals to 2 and L equals to 100. So dy dt here, your dy dt is then going to be equivalent to 1 divided by 1 divided by 1 plus e to the power x. X is 2. They told that x is 2, guys, don't forget. And then L equals to 100 shit, multiplied by the L dt. We've already discussed it, that it's going to be positive 5 plus, and then our L, it's 100 multiplied by e to the power negative 2 divided by what? By just 1 plus e to the power negative 2, and then you square this multiplied by the x dt. The rate is going to be negative 3, and then your dy dt is then going to be equivalent to what? To negative 27 comma 0941 units per second. So it's going to be units multiplied by second to the power negative 1. So that's units per seconds. That's units per second, or unit per seconds per second, just like that. So this is your rate of change in y. So this is going to be negative that, and then yeah, that's it. So let's quickly check some examples under activity 12. We are given that the volume of a right circular cylinder is given by V equals to pi r squared height, where r is the radius and h is the height of the cylinder. Find the rate of the volume. So you're told that you should find the rate of change of volume. Find the rate of change of volume. So that means we should calculate the rate of change, right? We should apply our rate of change formulas, and then V. If the radius increases at a rate, so the r is increasing at that rate, and the height decreases at that rate, this is decreasing. When r equals to 6 and h equals to 10 centimeters. So let's go. So let's start by differentiating partially, then we'll just substitute into our equations. So this means that partial derivative of v with respect to let's first differentiate with respect to r. So we're differentiating this equation with respect to r, this equation with respect to r, so meaning that h is a constant as well as pi. So that means we are going to get 2 pi rh, 2 pi rh, and then we are told that the rate at which what changes, radius changes, the rate at which r changes with respect to time is equivalent to what? It increases at 0.2, right? And then now let's find out about our partial derivative of v with respect to h. This is going to be equivalent to how much? So we're differentiating this equation with respect to h, meaning that r is a constant as well as pi. So we're just going to get that pi r squared. And then our rate, the h dt, is equivalent to what? They told us that h decreases at 0.3. So negative 0.3 is our rate there for h. So let's write our formula now. So the rate of change of volume formula is going to be this: the rate of change of volume. So dv dt is equivalent to what? To partial derivative of v with respect to r multiplied by the r dt plus partial derivative of v with respect to h multiplied by the h dt, just like that. And then we do this, and then we substitute from here. We're going to substitute our all of these things. So rate of change of volume is going to be equivalent to, we just substitute 2 pi r. So we're going to substitute 2 pi rh multiplied by the r dt plus what? Plus this is pi this is going to be pi r squared multiplied by dh dt. So let's not forget that we're told that r is equivalent to 6 and height is equivalent to 10. So dv dt is then equals to, so we're just going to substitute those values, multiplied by r, which is 6, multiplied by our h, which is 10. And then, yeah, let's just write 6, 10. And then multiplied by our dr dh is, dr dt is 0.2 plus pi, our r is 6 r squared multiplied by dh dt, it's negative 0.3. And then we just press on our calculator, we'll get that dv dt is going to be equivalent to 41,469 cubic centimeters per second. So this is going to be the rate of change of volume for this question. So yeah, we successfully answered this question. So yeah, that's it, guys. Whenever they say rate of change of volume, you just know that you're calculating now rate of change. You just need to manipulate the formula with the use of the equation that you're given, and then you do the substitution, you get your final answer. So let's see another question first. So the other question that we have now will be this one. This is going to be the question that we are going to discuss right now. All right, let's quickly do this question. So we're told that the frequency of vibration of a guitar string is given by f1 over 2 L multiplied by root of T over density, where L is the length of the string, T is the tension, and P is its density. Determine the percentage change. So the question says determine the percentage change. So we are determining the percentage change now in frequency f if tension T increases by 2% and linear density P increases by 3% while the length remains constant. So that's our thing there. So that's our question. So we are told that L is what, or L remains as a constant. Okay. So that means changing L is 0, changing the length, percentage change in length is 0. That's what this statement says, while L remains as a constant. So they're saying that L doesn't change in terms of percentage, but instead the tension increases by 2% and then the density increases by 3% as well, but L doesn't change. So that means change in L is going to be 0. All right, so let's start. So guys, feel free to pause the video so that you can work out on this problem on your own, give it a try, and then see if you will also get the same answer. So yeah, so we're going to differentiate this F thing with respect to L, and then with respect to T, and then with respect to P there. So we'll get 3 different types of equations. So yeah, let's start. So partial derivative of F. So partial derivative of F with respect to let's start with we can start with L, it's fine. Let's start with L. So when we start with L, we're going to take L up, that will become L to the power of -1. Then we differentiate, we will get something like negative 1. We'll get something like -1 over L squared multiplied by a root of T divided by density, just like that. And then now we can again differentiate our F. So now let's differentiate partially with respect to T. with respect to t, right? So this is going to be what? So if you see this big root, if you make t to have its own root and this density p to have its own root, then that means you're going to have t to the power 1 over 2 divided by root of p. Understand? So from there, we are going to differentiate with respect to t. So you will have t to the power 1 over 2 and then divided by root of p, or divided by square root of p. So we differentiate with respect to t. That means L and p are constants, so that t to the power of half over 2, it will be 1 over 2, which will multiply this, and then we also subtract 1 from 1 over 2. So we end up getting that 1 over 4. We'll end up getting 1 over 4 L, right? 1 over 4 L multiplied by t to the power negative 1 over 2 divided by root of p, or density p there. And then yeah, that would be it for that one. And then now we need to differentiate again partially with respect to density now, with respect to density. So that means we're still going to do the same thing. We're going to say root of t and then divided by root of p. So we can take root of p up there. It will be p to the power negative half over 2. Negative 1 over 2. Negative 1 over 2. So then we differentiate t, and L will be constants. So you will get negative half multiplied by what? Multiplied by this half here. It will be negative 1 over 4. Negative 1 over 4 L multiplied by what? Root of p, root of t, sorry, root of t divided by, so remember p will be there and it will be having negative half, right? Negative 1 over 2, exponent of negative half. If we subtract 1 from negative 1 over 2, we will get negative 3 over 2. We take p down, it will become density to the power 3 over 2, just like that. We have a positive exponent. So they say that determine the percentage change, right, in frequency, and if tension increases by that. So tension is increasing by 2% and then linear density is increasing by 3%. Why? The length remains constant, so L does not change. So change in L is 0. So our change in L is equals to 0. And then what? We calculate for this one. This is going to be no, we substitute. I mean, like, we just take the what we are given there. The percentage change in t is 0.02. So percentage change in t is equivalent to 0.02 t. And then this other one is what? It's for density. They say density increases by that, so it's positive. So small change in density is what? 0.03 density, just like that. So now we can rewrite our equation in this following manner. So yeah, let's go. So we are going to start. All right, so what? So now let's write our percentage change formula of the frequency. There's a percentage change formula. So percentage change formula is going to be equivalent to partial derivative of f with respect to L multiplied by change in L plus partial derivative of f with respect to what? With respect to t multiplied by change in t plus partial derivative of f with respect to density multiplied by change in density, or percentage change in density. So this is how our formula is going to look like. From there we are just going to substitute, right? So partial derivative of f with respect to L, we're just going to substitute this. So this is negative 1 over L squared multiplied by T over density, and then multiplied by our small change, of course, our small change there. So let's substitute. Our small change is 0, and then plus this one, partial derivative of f with respect to t is this one, so we're just going to substitute that there. So when we substitute it here, it's going to give us something like 1 over 4L multiplied by t to the power negative half divided by root of p, and then this, and then we multiply by the change there. The change is just positive 0,02 t, and then we say plus, we substitute the last one there. It's going to be negative 1 divided by 4L multiplied by root of t divided by density to the power 3 over 2, and then we multiply by 0,03 density. Okay, just like that. So from here we can see that 0 by this is going to be 0, so this term is out. So from here we should take out f. So we're going to take out 1 over 2L root of t over p as our common factor from this. So we must make it a common factor. But before we do that, let's write it clearly. So we're going to multiply t by that. You are going to get that, okay, small percentage change in f is going to be, so remember this is 0. So here when we multiply by t by that, negative 2 and 1 which comes from here, we'll add each other and you'll get t to the power positive half, right? And then half of t, that means that's a root of t. That will be root of t after you have multiplied, and then I'll just write, since t will now have a root and this will have a root, so then I'll just write root of t over p. I'll just rewrite it like 1 over 4L multiplied by a root of t over p, just like this, just like that, and then multiplied by 0,02. Makes sense, right? And then from there I am going to also multiply again for this case. So density is going to multiply this. So since this p has positive 1 there, so that positive 1 will get subtracted from this negative 3 to, from this 3 over 2 we'll get positive half. So that's going to be p to the power half will be then root of p. So since root and root there, then I'll just rewrite it the same way I did there on the other side. So this is going to be let's just say plus into what, into 1 over 4L multiplied by the root of what, of t divided by density multiplied by 0,03, just like that. Okay, so here we are going to take out 1 over 2L root of t over p as our common factor from this, so that we can see our percentage change of f. So percentage change of f, when we take 1 over 2L multiplied by the root of t over density as our common factor, will be left with 1 over 2 multiplied by 0,02 minus 1 over 2 multiplied by 0,03, just like that. Makes sense, right? So we know that 1 over 2L multiplied by root 2 over p is what is equivalent to f, right? From the given equation, this is f, so we're just going to replace it by f. So percentage change of f is going to be what? F multiplied by, so when you use your calculator to press what's inside the bracket, you'll get that this is equivalent to negative 0,005. So that's our, so if I can rewrite this again further, this is negative 0,05, right? 0,0, let's just confirm. So this is 0.5, 0.5, negative 0.5% of f. That is to say, if we conclude this, we can say that there's gonna be a decrease by, so our f is going to decrease by 5%. So therefore our f decreases by 0.5, sorry. Therefore there is this decreases, this means this decreases by what? By 0.5%. It decreases because of this negative sign here, so it decreases by 0.5%. So that's it, we've answered that question. So let's quickly check another one, and then we manipulate just like that. Yeah, so feel free to pause the video, try this question on your own, and then resume later to check the memo, of course, because you're not watching a movie, right? Or are you? Is this a movie to you? I hope not. Yeah, anyway, for this other question, we are told that for gas confined in a container, the pressure P is given by P equals to mTV, mt divided by V, where m equals to 20 and m is a constant. Find the rate at which P is changing if the temperature T is increasing at 2 degrees Celsius divided by per hour. If temperature is increasing at 2 degrees Celsius per an hour and the volume is increasing at 0.2 meters cube per an hour at the instant when T equals 22 degrees Celsius and V equals to 12 cubic meters. So the question says, so let's go back to the question. The question says we should find the rate at which P is changing. So the rate at which pressure is changing. So we are required to find the rate of change of P. So yeah, let's go. This should be easy. Yeah, feel free to give it a try there, and then you'll resume the video to check the memo after that. So yeah, so let's rewrite our partial derivatives first. So partial derivative of P with respect to, remember m is a constant, so with respect to T is going to be what? So we're going to differentiate this equation with respect to T, so meaning m and V are constants, so this is just going to be m over V, right? This is going to be m over V. And then we also differentiate again partially, so the derivative the partial derivative of what? Of P with respect to V is going to be equivalent to, so m and T now are constant, so you can take V up and say V to the power -1, then you differentiate, you will get that this is going to be equivalent to minus mt divided by what? V squared, just like that. So how about our rates, guys? Let's write our rate. So dt is what? So the rate at which temperature increases, they say it's 2 degrees Celsius, so this is just going to be our 2. And then the rate at which V increases, the rate at which V increases with time is what? It's 0.2. So yeah, now we can just write our formula and then plug and play there, all of these things. So that means Now let's answer the question of saying that find the rate at which P increases. So we're finding the rate of change of P. So dP dt is equivalent to partial derivative of P with respect to T multiplied by dt plus what? Plus partial derivative of P with respect to V multiplied by dV dt. So this is going to be your rate of change. So now let's just substitute our partial derivative of P with respect to T, M over V, then that and that. We just plug and play everything right now. So when we plug and play, this is how it's going to look like. So partial derivative of P with respect to T, this is M over V. This is going to be kept M over V multiplied by dt. So we'll substitute this rate after when we're substituting all the values to make it look nice. Okay, now let's substitute our partial derivative of P with respect to V. This is going to be negative mt over V squared multiplied by dV dt. So we were told that our M is equivalent to 20, and then temperature equals to 22 and V equals to 12. So we're just going to substitute all of those values here, and then we get our answer. So our M there, this is going to be 20 over 12 multiplied by dt. So this is going to be 2 plus what? Minus 20, that's your M, multiplied by, this is multiplied by T. So our T is 22. Temperature equals to 22 divided by V, which is 12 squared, multiplied by 0.2, which is our rate. And then we use our calculator there. We will find that our rate of change of P is going to be equivalent to what? 2,72 pascals per hour. So this is going to be your answer. So yeah, this is to be your answer for that question. So yeah, all right, let's quickly check other things then. Let's quickly check other questions. So another question is this one. We have if theta equals to KHL divided by root of V, where K is a constant, and there are possible errors of plus minus 1% in measuring HL and V. Find the maximum possible error in the calculated value of theta. So what is this? They said find the maximum possible percentage error. So we are calculating the maximum percentage change. So you should remember that when we are taking when we are substituting our values of percentage changes of these different variables, we should take the sign that makes the equation positive, or the multiplication of the partial derivative and the change to be positive. So yeah, let's start. I'll show you what I mean by that. So the possible errors of all of these ones, HL and V, are 0.01. So all of them, HL and V. So let's start. Let's start by differentiating partially with respect to H, with respect to L, as well as with respect to V. And then we'll just substitute our changes thereafter. So yeah, let's go. So partial derivative of what? Partial derivative of theta. partial derivative of theta with partial derivative of theta with respect to h is going to be equivalent to what? This is going to be equivalent to, so if k, l, and v are constants, then we differentiate with respect to h, then we're just gonna get kl, right? We're just gonna get kl divided by root of v. All right, so now we should differentiate theta partially again, differentiating theta partially with respect to l. This is going to be what? So h, l, and v now are constants. hk and v, hkv are constants. So we're differentiating with respect to l. So this is just going to be kh, right? This is going to be just kh divided by root of v. And then we do that again, we differentiate partially with respect to v, right? With respect to v. Now, so meaning k, h, l are now constants, then we're just differentiating with respect to v. So you can take v up there, it will become v to the power negative 1 over 2. Then we differentiate with respect to that, you will get negative 1 over 2 khl divided by, so remember v here will be v to the power negative half, right? So if you subtract 1 from negative half, you will get negative 3 over 2. We write that in positive exponent, meaning that we'll take v down, it will become v to the power of 3 over 2, just like that. So our our percentage change in h, so they told that percentage change in h is equivalent to plus minus 0,01 h, and then the percentage change in l is what? Is 0,01. It's plus minus 0,01 l, and then the percentage change in v is equivalent to what? Plus minus 0,01 v, just like that. Okay, now let's write our formula for the maximum possible percentage change. So our formula for the maximum percentage change this is going to be the following. Maximum percentage change there is going to be equivalent to partial derivative of theta with respect to h multiplied by change in h plus partial derivative of theta with respect to l multiplied by change in l plus partial derivative of theta with respect to v multiplied by change in v. And then from here we're just going to substitute all the formulas that we have here, and then as well as the changes to get the maximum percentage change, of course. So yeah, let's go. So our maximum percentage change of theta is going to be equivalent to, we substitute our k l over root of v, which we got here. Remember we already calculated that, and then multiplied by the small change, the percentage change, I mean percentage change, and then plus, so this one of partial derivative of theta with respect to l is kh over root v, so that's going to be kh over root of v. So kh over root of v, sorry, this is going to be kh over root of v, kh over root of v multiplied by change in l, percentage change in length. That's let's just substitute it like that first, and then okay, and then here we are going to substitute our this one. Okay guys, I've just realized, why don't we just substitute so that we avoid long steps? I can say that let's just substitute our changes, like let's just substitute our percentage change in this thing so that we avoid long things, because I can say that it's unnecessary to make this long, guys. It's unnecessary. So remember about the signs here. We must take the one that when we multiply this and this, we get a positive. So this is already positive. That means we must take 0.01 h as positive. 0.01 h as positive. Then we say plus, we substitute the other one of kh divided by root of v multiplied by percentage change. So remember, so since this one is positive, so we must substitute the percentage change as positive, so that when we multiply those two, we get a positive answer. So that's going to be plus 0.01 L, and then we say plus again, we substitute what? We substitute the other one of -1/2 khl divided by v to the power 3/2, just like that, multiplied by our change. So just because of this partial derivative is negative, we must make sure that when we take the change of v here, it must be negative, so that when it multiplies with this negative, we get a positive. So that's our maximum. That's us maximizing the thing there. So that's going to be negative 0.01 of v, just like that. So remember guys, from this step, we just need to multiply h with that, and then l with that, and then v with that, as well as these two signs. So let's go. So partial derivative. So maximum percentage change of theta is going to be equivalent to, so when we multiply h with that, we're going to get klh. We're going to get that klh or khl. So let's write this khl divided by root of v, right? Multiplied by 0.01. Because I've already multiplied h with that thing, and then from here I multiply l with this, I get khl, right? I'm going to get khl divided by what? Divided by root of v multiplied by 0.01. And then here, negative and negative will multiply each other, we'll get a positive, and then what? 1/2. So here we have 1/2. So I multiply v with this. So since v has a positive 1 exponent here, so that positive 1 exponent will get subtracted from this 3/2. We'll end up getting 3/2 minus 1. It will be positive half, and then that will make this root of v. So this will be khl divided by root v multiplied by 0.01, just like that. So now we should take this khl as our common factor, so that we can equate it to theta. Khl divided by root v as our common factor, so that we can equate it to theta. So our maximum percentage change from here, is going to be khl divided by root of v, just like this, and then we multiply this. So I'm taking out this as a common factor out of these three terms. So when I take it out here, I will be left with just 0.01 plus this case is going to be 0.01 as well, and then plus here when I take khl, I'll be left with 1/2 by that. So plus 1/2 0.01, just like that, and then that means our maximum percentage change of theta is going to be equivalent to what? Remember, khl divided by root v is equivalent to what? To theta. So that means here we can substitute that our theta, and then you do the calculator there to get the number inside the brackets. You'll find that it is equivalent to 0,025, right? And then so this means that maximum percentage of theta is equivalent to 2,5% of theta. So that's just 2,5% of theta, right? So we successfully managed to answer this question, which was the maximum possible error in the calculated value of theta. So we got 2,5% of theta. All right, so let's go again. Let's do another question. So for this other question, so for this other question is that we have the period T for small oscillations of compound pendulum is calculated from the formula T equals to 2 pi k, where k is the radius of gyration about the point of oscillation O, and h is distance between O and the center of gravity. If G is a constant but the measurements of H and K are subject to errors of plus minus 1% and plus minus 2% respectively, that means that the percentage change in K is plus minus 1 and then the percentage change in K is plus minus 2 respectively. So calculate the maximum error in the calculation of T. So we are again calculating the maximum percentage change of that thing. So we are told that, okay, let me look for that word here. There is something that they mentioned here. Okay, K is the radius of gyration and H is that the distance of gravity. If G is a constant, so they told us that G is a constant, so G is a constant, so that means the only variables that we're going to differentiate partially with respect to is just K and our H. So let's go. So let's start by writing our partial derivatives. So partial derivatives of K. So partial derivative of K. So partial derivative of T with respect to what? With respect to K. Let's start with K first. So when we differentiate this equation with respect to K, meaning that H and G are kept as constants, we're just gonna get 2 pi divided by root of H multiplied by G. We'll just get, this is 2 pi divided by root of H multiplied by G, and then that's it. And then we differentiate again partially. So partial derivative of T with respect to to H now, to H is going to be equivalent to what? So remember, now we're differentiating with respect to H, né? So we are going to make H to have its own root. So meaning that this is going to be root of H multiplied by root of G. And then we take root of H up there. This will become H to the power negative half. H to the power negative 1 over 2. Then we differentiate with respect to H, keeping K and G as constants. You will get something like, okay, it will be 2 pi. So that 2 pi will still be there. So 2 pi will still be there, and then you multiply by what? 2 pi k will still be there. 2 pi k will still be there, and then okay, oh, maybe I think this might confuse you. Let me rewrite this equation first nicely so that you don't get confused. Okay, so T here is going to be the same as 2 pi k multiplied by H to the power half divided by root of g. Does this make sense? I hope it does, right? Because the all right, to avoid confusion, let me just rewrite this simple again so that I don't make people to get lost. So this is root of h multiplied by root of g. So you see what I wrote here is the same as that. So this is again equivalent to 2 pi k multiplied by h to the power negative half divided by root of g, just like that. So this is the same, right? This is the same as that. So I just rewrote h using exponents, root of h using an exponent. So this, at first it was positive 1 over 2, and then I took it up, it became negative. So now I'm going to differentiate partially with respect to h. So this is going to be negative 1 over 2 will multiply here, so 2 and 2 will cancel out. We'll end up getting that partial. You will end up getting that partial derivative of t with respect to h is then going to be equivalent to negative pi k, and then you subtract 1 from this negative half of half, you will get negative 3 over 2, right? You will get negative 3 over 2. You write that using positive exponents. This is root of g that was there. That's going to be h to the power 3 over 2 when I write it using a positive exponent. So I'll take it down so that I can write it as a positive exponent, and then it will look like something like what I wrote there. So yeah, that's it. So now let's quickly write the percentage change, right? So the changes here, the change that we have, so h, let's start with the one of k. So with respect to k, percentage change in k is equivalent to what? 0. Okay, it's plus minus 0, 0, 0.02 k. That's the change. And then the percentage change in h is plus minus what? 0.01 h. So this is the change, and this is the change of that, right? Makes sense? So yeah, now let's write our maximum percentage change error formula with regards to this equation. So this is going to be something like okay, let me also reveal the formula. So this is going to maximum percentage change of t is going to be equivalent to partial derivative of t with respect to k multiplied by change in k plus plus partial derivative of t with respect to h multiplied by what? Multiplied by change in h, just like that. So now we have the formulas, and we're just going to substitute that. So let's do the substitution now. So this is going to be partial derivative of t is going to be then equivalent to, we're just substituting now. This is 2 pi divided by a root of h multiplied by g. This is then multiplied by the change. So because of this one is positive, and remember we're looking for maximum percentage change, so we have to take the sign that when we multiply this and this, we get a positive value. So we're going to take the one of positive. So that means the sign for the change is going to be positive. So that means here we're just going to substitute 0.02 k, and then we close, and then we say plus. Here we copy this guy. So when we copy that guy, this is how this is going to look like. Negative pi k divided by a root of g multiplied by h to the power 3 over 2. Multiply this by our change. So you can see that this partial derivative is negative, right? So that means when we take our change here, the sign of the change in h, we have to take the one that is negative, so that the negative and the negative can multiply each other to form a positive. So that means here we're going to say negative 0,01 h. So now we should take 2 pi k, we should take 2 pi k over root of hg as our common factor. So before we do that, let's then just multiply. Let's multiply first. So we can see that when we multiply here by k, this k multiplies there, we'll get 2 pi k divided by root of hg. But then this side, when we multiply by h, yes, we will get what, since this is h to the power half, this will form 3 over 2 minus 1 from there, and then this will be root of h, because 3 over 2 minus 1, it's 1 over 2. So this will end up being root of h when we've multiplied with h there. But then we won't have a 2 there. We won't have a 2. And remember, our goal is to end up taking 2 pi k divided by root of hg as our common factor. So since we won't have 2 there, 2 here, so we need to cook 2. So we are going to manipulate by cooking. So let's cook. So when you cook there, you must cook that 2. So that means we're just going to multiply this thing, this term by what? By a 1, a cooked 1. That works for us. So that means we're going to multiply by 2 over 2. So if I multiply this term by 2 over 2, 2 over 2 is 1, guys. 2 over 2 is 1. So I'm not changing the equation. But then we can make use of this 2 over 2, right? In a way that it helps us to answer this question. So let's go. So now we are going to multiply there. So this means partial derivative of t is going, maximum percentage change is going to be equivalent to what? So when I have multiplied k and that, I will get 2 pi k divided by root of hg, and then I close. I will be left with 0,02, and then plus, so let's again multiply negative and negative, we'll get what? Positive, right? And then we take 1, 2 here. So let's take this numerator of 2 to come here. So this will be 2 pi k divided by root of, remember we said when we multiply h with this, we'll end up getting root of h, or h to the power of our half, right? So that root and root multiplying each other will just have one root, and then those things multiplying each other inside the root, sorry. So this will end up becoming hg, and then just like that. Now we are left with what? With this. So remember, we took 1, 2 here, which is this. So we're left with the 2, which was the denominator. So we are left with 1 over 2 multiplied by this 0.01. And then, yeah, just like that. Now we can answer our question. So we're going to take 2 pi k as our common factor here. So maximum percentage change in t, it's 2 pi k divided by root of hg. So we're taking it as a common factor, we'll be left with just 0,02 plus what? Plus 1 over 2 into 0,01. And then we know that 2 pi k divided by root of hg is equivalent to what? To t, the period. So we can substitute the period there. So maximum percentage change in t is equivalent to t multiplied by what? So when you use the calculator there to press the things inside the bracket, you'll get 0,025. Therefore, your maximum percentage change there, it's what? Your maximum percentage change of t is 2,5% of t. And then, yeah, You have successfully managed to answer this question correctly in that way. So yeah, that would be it, guys. That will be it for that question. So yeah, that was it for this question. I hope you got it. That was not a bad one, because now you understand what is what. You can manipulate all of these things, right? So yeah, let's see if we can solve another one. So now we have, what? We have that the volume of water in a dam is determined by the formula V, which equals to 2 pi h 3d minus 3h. After it has rained, the water is flowing into the dam, resulting in an increase of volume at a rate of 35 cubic meters per hour due to the inflow of water. The diameter d of the dam is increasing at 0.25 meters per hour. Find the rate at which the height of the water is changing at the instant where when d equals to 20 meters and h equals to 6 meters. All right. So for this one, let's just first start by multiplying out there to avoid this bracket thing. So let's write it in this following manner. So let's rewrite our given v equation in a way that we multiply. To avoid that, we'll get 6 pi hd 6 pi hd minus what? 6 pi h squared. 6 pi h squared. 6 pi h squared. Yeah, 6 pi h squared. So this I've just multiplied out there to eliminate the brackets, so that I avoid using product rule when I have to differentiate, because somehow I will have to use product rule, and that's gonna be long. So let's just rewrite this equation in that way that I've written it. So now, yeah, let's manipulate it. Now let's try to answer the question. So what are we given here? So in this question, we are given that the resulting increase in volume at a rate of, okay, the water is flowing into the dam, resulting in an increase of volume at a rate of 35 cubic meters per hour. So we're already given the rate at which the volume changes. Okay, we're given that. And then what else are we given here? We are also given that the dam is increasing at the diameter of the dam is increasing at a rate of 0.25 meters per hour. So meaning we are given the rate at which d is increasing with time. The only thing that we're not given is the rate at which height changes with time. So let's solve this equation. So we are given the rate. The only thing that we are not given is the rate at which h changes. All right, let's start. So now let's differentiate partially with respect to h and as well as with respect to d. So let's go. So let's start. Partial derivative of v with respect to what? We can start with d first. So when we differentiate with respect to d, here on this equation, we are going to just get 6 pi h, right? And then the other one will be 0. So this is going to be just 6 pi h. And then we differentiate again with respect to what? To h. So partial derivative of v with respect to h is then going to be equivalent to, when we differentiate this with respect to h, we get 6 pi d, right? 6 pi d, we get 6 pi d minus 12 pi h. So you're going to get 6 pi d minus 12 pi h when we differentiate this v with respect to h. So now let's write our rate. So the rate at which the diameter increases with time is given to us as 0.25. You remember that they say the diameter of the dam is increasing at 0.25 meters, so that's the rate. And then now the rate at which h increases or decreases with time. So the rate at which height changes with time, we are not told. So this is what we are looking for. And then we're also given that the rate at which volume changes is increasing by 35 meters is what is 35 cubic meters per an hour. So yeah, let's go. So now we can rewrite our equation. So partial derivative of v. So partial derivative of v. So partial. Now I'm just writing the. Now I'm writing the rate of change of v formula. So I'm writing the rate of change of formula for v. So now that means this is the v. This is going to be the v. The t, right, is equivalent to the partial derivative of v with respect to d multiplied by change in multiplied by the rate at which the diameter changes with time. The rate at which the diameter changes with time plus partial derivative of v with respect to h multiplied by the rate at which h changes with time. So yeah, let's go. So we are told that the rate at which volume changes with time is equivalent to what? 0.35. But before we substitute anything, let's just substitute the formulas for those partial derivatives. So let's still write this as partial derivative of v with respect to time is equivalent to partial derivative of v with respect to d. So we already found this as what? As 6 pi h multiplied by what? Multiplied by the d, the rate at which diameter changes with time, plus, okay, this one we already found it as 6 pi d minus 12 pi h multiplied by the rate at which h changes with time. So we were told that the rate at which volume changes with time is equivalent to 35. So now I'm just going to substitute everything here. So this is going to be 35, which is equivalent to what? 6 pi multiplied by, we were also told that h is equal to 6 and d equals to 20. So h equals to 6. So I'm just going to substitute my 6 here. And then I close. And then the rate at which the diameter changes with time, we were told that it is equivalent to 0.25. It's increasing at that. So this is 0.25. And then we say plus, we say 6 pi. We were told that the diameter is equivalent to what? To 20 and h equals to 6. So this is going to be 2 pi 20 minus 12 pi. H is what? Is 6, right? So 6, and then we close. And then the h, the rate at which h changes with time is what we are looking for. And then you use your calculator there. You will you'll say 35 minus this divided by this whole bracket, and then you'll get that the h dt is going to be equivalent to what? 0, 0.446 meters per an hour. So yeah, this is what you're going to get. So yeah, the rate at which the water is, the height of the water is changing, it will be increasing. Therefore this increases at a rate of, therefore that means H increases at a rate of 0.04. So therefore that means, therefore this means that H increases at a rate of 0.0446 meters per hour, just like that. So yeah, this will be your final answer for that question. And then what else should we then discuss? Okay, we also have another question here, which is this one. So let's just quickly do it and then see if we can get something there. So let's go. All right, we're told that for gas confined in a container, the pressure P is given by the equation P, which equals to mt over V Pascal, where m is a constant equal to 20, T is the temperature, and V is the volume of the gas. A maximum pressure change of more than 4% will result in an explosion. So they're saying that a maximum pressure change of more than 4% will result in an explosion. Take note of that. Determine whether the change will cause an explosion. So determine whether the change will cause an explosion when temperature of T changes by plus minus 3% and the volume changes by plus minus 2%. So let's calculate the percentage change in pressure and see if it will be greater than or less than 4%, so that we can see that there will be an explosion or not. So yeah, let's go. So let's start differentiating partially like always. So we're going to differentiate partially on this equation of P. So remember that m is a constant, guys. So partial derivative of P with respect to what? With respect to T first, this is going to be m over V. And then we differentiate partially again, partial derivative of P with respect to V. How much is it going to be? This is going to be negative mt over V squared. So our change, the percentage change in the temperature is plus minus 3%. So percentage change in temperature, that's plus minus 0.03%, 0.03 I mean, of T. So it's 3%, which is 0.03 of that. And then the change in V, so percentage change in V is going to be equivalent to plus minus 0.02 of what? Of V, just like that. So now let's rewrite our equation of the maximum, because this thing is saying that determine whether the change will cause an okay, so this is not the what, let's see, this is, yeah, we should calculate the determine whether the change will cause an explosion when the temperature T changes by that. So we should calculate the maximum, because they said a gas maximum pressure changer, because they said a gas maximum pressure change of more than 4% will result in explosion. So for us to be able to determine that there will be an explosion, that means we should also calculate the maximum change in pressure there. So let's go, let's write down our formula. So maximum percentage change of P is going to be equivalent to the partial derivative of P with respect to T multiplied by change in T plus partial derivative of P with respect to V multiplied by the change in V. Now it's time for substitution. So change in P is then going to be equivalent to what? M over V multiplied by the change. Remember here, when we substitute our change in maximum percentage change, we take the sign that makes this multiplication positive, the result of this multiplication positive. So since this one is positive, we're going to take positive there as well. So that means we're going to take 0, 0.030, and then we say plus, and then we take the other one, which is going to be negative m over mt divided by v squared, right? This is multiplied by what? So the change here, the sign that we're going to take is negative because of, we must make sure that the multiplication of this and this is positive. So since we have a negative here, we must take another negative there so that we get the positive answer when we multiply. So this is 0, 0.02 v. Makes sense, right? So now what we need to do is just to take, since p equals to mtv, t over v, so we're going to make mt over v as our common factor here. So we should take it out as our common factor. So to be able to do that, we have to first multiply here. So we're going to multiply this t by that. We'll get that this is mt divided by v multiplied by 0, 0.03, and then this will be plus, because of negative and negative will form a positive, and then when we multiply this v by that, one v will chop one v there, and then we'll just be left with mt over just v multiplied by 0, 0.02. And then we can now take mt over v. We can now take mt over v as our common factor. We'll be left with just 0, 0.03 plus 0, 0.05. And then we multiply. But remember that mt over v is equivalent to what? Mt over v is equivalent to p. So we can substitute it here. So meaning that partial derivative of p is what? It's p multiplied by what? By 0, 0.05. So you can see that this is the same as 5%. 5% of p, right? And let's go back to something here on this statement. They say that a maximum pressure change of more than 4% will result in an explosion, right? So let's check our maximum percentage change. So our maximum percentage change is 5%. What does it mean? It means that it is more than 4%, and it means that it will cause an explosion. So therefore we can conclude that it will cause an explosion, just like that. So that's it. You will be done with that question. So let's quickly check if we can do another question again. Remember to pause the video so that you can work out on this problem on your own, and then resume later to check the memo. So this question reads as follows. The volume of water in a dam is determined by the volume V equals to 2 pi h into 3d minus 3h. After it has rained, the water is flowing into the dam, resulting in an increase of height h at a rate of 0.06 meters per hour, while the diameter of the dam is increasing at the rate of 0.25 meters per hour. Determine the rate at which the volume of water is changing at the instant when d equals to 20 and h equals to 6 meters. So the question says we should determine the rate of change of volume. So that means we are going to manipulate that formula of rate of change, so with the use of these formulas given. So as always, guys, let's start differentiating partially with respect to d and h respectively. So let's start. So the partial derivative, or maybe we can just first start by multiplying before we do that. Let's just first rewrite our given formula of v in this following way. So v equals to 6 pi hd, 6 pi hd minus 6 pi h squared, 6 pi h squared. So from this equation that I just wrote here, let's differentiate partially from it. So partial derivative of v with respect to h is going to be equivalent to 6 pi d. It's just going to be equal to 6 pi d minus 12 pi h, right? And then let's differentiate again partially with respect to d in this for this time around. So this is just going to be 6 pi h, right? 6 pi h when we differentiate with respect to d. And then the rate at which height increases, height increases with time is dh dt, which is going to be equivalent to what? 0,06. So we're given that an increase of height at a rate of 0,06. So we were given that. And then how about the one for the rate at which the diameter increases with time is equivalent to 0,25. So now we can just differentiate, now we can just substitute, right? We can just substitute. So before we substitute, let's write our rate of change formula of volume. So the rate of change of volume is going to be equivalent to the following. The rate of change of volume is going to be the rate of change of volume with respect to time is going to be equal to the partial derivative of v with respect to h multiplied by the rate at which h changes with time plus the partial derivative of v with respect to the diameter multiplied by the rate at which the diameter changes with time. And then from there we can see that we already have the partial derivative of v with respect to h. So we're just going to substitute 6 pi d minus 12 pi h multiplied by the rate at which h changes with time. So the rate at which h changes with time, I'm just going to write this. I'll substitute after this step. So I'll substitute the values after this step, so 6 pi h, and then what? The rate at which the diameter changes with time, so dd dt. And then from here, partial derivative of v with respect to time. So we were told that the diameter equals to 20 and h equals to 0.6. That means when there is h, we're going to substitute 6, and when there is d, we're going to substitute 20. So, and then the derivative of h with respect to t is that one, dt is that one. So now let's just substitute everything and get our answer. So 6 pi of 20 minus 12 pi into 6, and then we close. Then the h dt is 0,06. Then plus, again we substitute here. This is going to be 6 pi of h which is 6, and then we close, multiplied by 0,06. 25, just like that. And then you're gonna punch in your calculator. You should be able to get something like 37,32 meters cubic meters per hour. So this should be your answer. So that this means that then we can conclude that therefore volume increases at 37,32 cubic meters per hour. So that's what you're going to conclude from this question. So yeah, that was it for that question. Let's quickly check another question. So another question is this one. So we are given that the area of the triangle is given by area equals to 1/2 xy sine theta. The variable x, y, and theta are shown in the diagram below. Here's the diagram. And then suppose that x increases from 25 centimeters to 25,01 centimeters. Theta decreases from pi over 2 to 2 pi over 9, and y remains unchanged at 23 centimeters. That means 23 centimeters, we can keep it as a constant, so we don't have to also it means that the small change in y is 0. So yeah, so calculate the change in the area of the triangle and determine if this change is an increase or decrease. So let's go. So they told us that y remains unchanged, so y is a constant. So meaning that when we are differentiating here, we should always acknowledge y as a constant. So yeah, let's go. So I can start by first, okay, let me scroll down. Okay, let me start by writing first our formula down. So we're given that our area is equivalent to 1/2 xy sine of theta. So we're going to differentiate partially like always. So the question said we should calculate the change in area, so we should calculate the small change in area. So this question is a small change type of a question, so we should calculate the small change. So yeah, let's go. So we should calculate the small change in area. Let's first start by calculating the partial derivatives first. So partial derivative of a with respect to, we can start by x. This is going to be equivalent, so we're going to keep our y and theta as constant. That means when we differentiate this is going to be just 1/2 y sine of theta, and then we differentiate partially again. So we differentiate the area partially again, but this time around with respect to y. So this is going to be 1/2 x sine of we are now going to differentiate with respect to theta cos of y is a constant. So now let's differentiate with respect to theta. So x and y are constants, so when we differentiate with respect to theta, then we should be able to get that 1/2 x y multiplied by cos of theta. Cos of x and y are constants, so we're only going to differentiate sine theta, and then it changes to cos of theta. So the small change in x is equivalent to what? To 0,01. They said x increases from 25 to 25,01. That means x changed by 0,01. And then how about the small change in theta? They said theta decreases from that to that. So that means small change in theta is equivalent to what? You can just say 2 pi over 9. You can just say 2 pi over 9 minus pi over 4 minus 2 pi. Okay, I'm pressing on my calculator now. 2 pi over 9 minus shift pi over 4. You have to get minus pi over 36. So that's going to be a small change in theta there, and it's negative. And then what they said, y remains a constant. So yeah, we have this. Now we just need to substitute in our formulas and then get the values. So yeah, let's go. So we are now going to say that small change in area is going to be equivalent to what? To the partial derivative of area with respect to x multiplied by the small change in x plus the partial derivative of area with respect to theta multiplied by small change in theta. Therefore, a small change in area is going to be equivalent to, we have this partial derivative, so we can just substitute that 1 over 2y sine of theta multiplied by small change in x plus, we substitute again, 1 over 2x y cos of theta multiplied by small change in theta. So I just substituted my partial derivative of area with respect to x here, and then substituted my partial derivative of a with respect to theta there. So I substituted this there, and then now I must substitute the value so that I can end up getting my small change in area. So like always guys, so the value of y, and so the value of y, they told us that it's 23 centimeters and it remains unchanged. So the value of x, because you can see that we must substitute the value of x as well as theta. So like always guys, like I've explained in previous questions, you always take the initial state of the variable before it changes, so, and regard it as your x. So that what I'm trying to say is that x is going to be the first value before it changed, and then theta is going to be the first value before it changed. That means x equals to 25 and theta equals to pi over 4. So now let's just substitute everything as well as our small changes to get our final answer. So therefore our small change in area is going to be equivalent to 1 over 2 multiplied by y. So y, we just agreed, they told us that it is 23, right? 23 multiplied by sine of what? Pi over 4. We told you that pi over 4 multiply the small change in x, which is going to be 0,01, plus we substitute again further, 1 over 2 multiplied by x. We agreed that it's going to be 25 multiplied by y, which is 23 multiplied by cos of pi over 4 multiplied by the small change in theta. That's going to be negative pi over 36 there, and then you press this everything there in your calculator. You should be able to get something like negative 17,6594 square centimeters. And therefore now we can conclude that the area decreases by 17.6594 square centimeters. So you can conclude by this statement. So I believe we successfully calculated what they wanted on this question because of that. So I hope you got it guys after giving it a try. So yeah, let's quickly check another one. So yeah, now we have v squared, which equals to rg tan theta, which is used in highway design, and g equals to 9.8 centimeters meters per second squared. So that's the gravitational acceleration, which equals to 9.8 meters per second squared is the gravitational acceleration. Okay, yeah. Suppose that r is decreasing at the rate of negative 0.02 units per second, and that v is increasing at the rate 0.071 unit per second. Find the rate at which theta is changing at the instant when theta equals to 0.175 and r equals to 4. So we should find the rate of change, right? So that means that we should manipulate the given formula of v squared into the one of rate of change. Okay, so let's go. So let's first rewrite that given equation in with respect to, or in the form of v, meaning that, well, I'm going to square both sides so that I end up having v as my subject of the formula, since that we're given that v squared equals to rg tan of theta. So when I square both sides, I'm going to end up getting that v is equivalent to rg tan theta, rg tan theta, rg tan theta, and this is inside a square root, just like that, rg tan theta, and that is inside a square root. Okay, so yeah, let's go. So now, like we have discussed, that the question said that we should find the rate of change of theta with respect to that. So rate of change at which theta is changing at the instant when theta equals to 0.175 and r equals to that. So let's go, guys. So let's first start by differentiating partial with respect to r as well as with respect to theta. So what we are going to get is the following. So let's go. So here, let's just rewrite this. I think it's gonna be easy like this if we rewrite this in the form of r to the power half g to the power of half multiplied by tan of theta to the power of half, like that. So let's give each and every term its own root, and then it's going to become like this. So now let's differentiate partially with respect to r and as well as with respect to theta, because g is a constant, right? So now let's write our derivatives. So partial derivative of v with respect to r is going to be equivalent to 1/2 r to the power negative half multiplied by g to the power of half multiplied by tan of theta to the power of half, just like that. And therefore, now let's go further and differentiate partially again. Let's differentiate partially again with respect to theta this time around. So we are going to get that r to the power half multiplied by g to the power half multiplied by, so for this one of tan, we're going to use chain rule, because of it's like this. It's like tan of theta here is inside the bracket, and we have 1/2 outside this. So when we differentiate, we're going to start with that 1/2 outside. This is going to be 1/2, then tan to the power negative to the power negative half, because of we'll subtract 1 from there, and then we'll get negative half. Then we then differentiate the inner function, which is tan. So that's going to be sec squared of theta, just like that. And then from here, okay, we have the derivative there. We have the partial derivative of that with respect to that. So what else is is needed here. So now let's analyze our equation again to see what we're given and what we're not given. Suppose that r is decreasing at a rate of that. So we're given that the r, the t, so the r, we're given that the r, the t is equivalent to negative 0.02. And then how about the rate at which, so the rate at which theta changes with time, it's what we are not given, we are looking for it. So we are also given that v is increasing at that rate, so we are given also the rate at which v changes with time. So now let's go and just substitute everything, but first let's write our formula at which let's write the formula for rate of change at which volume changes with time. So the rate at which the volume changes with time is equivalent to, so it's equivalent to the partial derivative of v with respect to r multiplied by the rate at which radius changes with time, plus the partial derivative of v with respect to theta multiplied by the rate at which theta changes with time. And then from here we're just going to substitute because we have everything. So before we substitute the values, let's first substitute all the equations. So yeah, this is going to be equivalent to 1/2 r to the power negative half multiplied by g to the power half multiplied by tan of theta to the power half, and then this is multiplied by the rate at which radius changes with time, plus we substitute again, we substitute 1/2 multiplied by r to the power positive half multiplied by g to the power half multiplied by tan to the power negative half multiplied by sec squared. So sec squared, we can just change it to 1/cos squared so that we can substitute our values on the second side. So cos squared of theta, so I just changed it into its reciprocal multiplied by the rate at which theta changes with time. So now we can just substitute everything. We were given that theta equals to 0.175 and r equals to 4, and then the rate at which volume changes with time is also given as 0.071. So now let's substitute all of those values. So here we're going to substitute our 0.071, which is equivalent to our 0.071, which is equivalent to 1/2 r. We're given it as what? As 4. R we're given it as 4, so this is going to be 4 to the power of negative half multiplied by g, which is 9.8 to the power positive half multiplied by tan. So our tan of our theta there is given as 0.175, and then this is to the power of what? This is to the power of 1/2, and then we can close, and then multiplied by the r dt, which is negative 0.02, plus we substitute further again. This is 1/2 r. We're given it as 4, right? So we're given r as 4 to the power half multiplied by g, which is just 9.8 to the power positive half again multiplied by tan of 0.175 to the power of negative half to the power of negative half multiplied by 1/cos. So cos of 0.175, and then this is to the power, this is squared. and then multiplied by the theta dt, just like that. So okay, from here we are going to take this term, this whole term, to the other side. So it's going to be negative. So when it goes to the other side, our left hand side, it will be positive, and then it adds with that. So you should be able to get something like 0,7758164,958,958 is equivalent to. So after taking this one to the other side, you'll get this value. So it's going to add with that other one because of it was negative on this other side. So when it goes on the other side, it's going to be positive. So you press your calculator again, you press only this term that multiplies the theta dt. You should be able to get something like 7,7,6,8,6,8,0,5,0,5,6,5, and then multiplied by the theta dt. So therefore your the theta dt is going to be equivalent to 0,01010 units per second. So that's what you're going to get there as your rate at which theta is changing, with time. So this is going to be your final answer. So I hope you get it. And anyway, let's quickly check another question fast. So the other question that we have here is as follows. So we have that the law of cosines for any triangle with sides of length x, y, and z, that we have z squared equals to, so this is the law of cosine, z squared equals to x squared plus y squared minus 2xy cos of theta. The triangle is shown below. So they've also shown us the triangle. Suppose that x is increased from 10 centimeters to 10,1 centimeters. Y changes from 15 centimeters to 14.8 centimeters, and theta remains unchanged at pi over 3. Find the change in z. So we should find the small change in z, right, with the use of the formula that we are given. So before we do the partial derivative, I just want to rewrite this given formula of z. I just want to make z the subject of the formula instead of z squared. So meaning that I'm going to square both sides. So let's go. So when I square both sides here, I will end up getting that my z is equivalent to root of is going to be equivalent to root of x squared plus y squared minus 2xy cos of theta, just like that. So now we can differentiate, right? So now let's then differentiate this one partially with respect to x as well as y, because of they told us that what remains unchanged and theta remains unchanged. So theta is a constant. So now let's differentiate partially. So the partial derivative of z with respect to x first. Let's start with respect to x is going to be equivalent to, so just because of we're differentiating a root, so let's differentiate using the skills that we used to use on the equations of differentiation on my previous videos. So we know that whenever we're differentiating a root, you just say put a fraction, and then on the denominator you say 2 root of what you were given. So 2 root of what we were given, which is x squared plus y squared, x squared plus y squared minus 2xy cos of theta. So on our numerator here, we're going to differentiate partially with respect to x. And the thing that we differentiate here on our numerator, it is what is inside the root. So when you differentiate what's inside the root partially with respect to x, that means y and theta are constant. So you're going to end up getting just 2x minus 2y, right? Minus 2y cos of theta. And therefore you differentiate partially again with respect to y now in this case. So now when we differentiate partially again with respect to y, we have to get almost similar things. So it's going to be the same thing, 2 root of what we're given as x squared plus y squared minus 2xy cos of theta. So then on our numerator here, you're just going to differentiate what's inside the root there. So that's going to be what? So with respect to y now means that x is a constant, x and theta are constant. So you're just going to get 2y minus 2x cos of theta, just like that. And then how about our small change? So we're told that the small change in x, so x is increased from 10 to 10.1. That means our small change in x is going to be 0.1. And then our small change in y is going to be equivalent to what? To negative 0.2. So now we can write our small change in z formula. So let's write our small change in z formula. It has to be equivalent to something like small change in z. So our small change in z is equivalent to the partial derivative of z with respect to x multiplied by the small change in x plus the partial derivative of z with respect to y multiplied by the small change in y. So now we can just substitute our formulas and then get our answer. So our small change in z is equivalent to what? So I'm just gonna copy now the formulas that I have above there, which is 2x minus 2y cos of theta divided by 2 square root of what? Square root of x squared plus y squared minus 2xy cos of theta. So that's the thing there, multiply by the small change in x plus I substitute my other things on the other side, which is 2y minus 2x multiplied by cos of theta divided by 2 root of x squared plus y squared minus 2xy cos of theta. So just like that, and then you multiply it by your small change in y. And then from here we need to substitute the values of x, y, and theta, and then as well as the small changes. So like always, guys, the value of x is going to be the value that is going to be the initial value before the changes. So that means x equals to 10 and then y equals to 15, because of always take the initial value before the changes. So that means y equals to 15 pi, and then theta equals to pi over 3. That's what I'm trying to say. So now let's just substitute everything like that. So that means our small change in z is equivalent to, now we're substituting x is 10, right? X is 10 and y is 15. So minus 2 into 15 multiplied by cos of what? Pi over 3. So this is going to be pi over 3, all divided by 2 root of x squared, which is going to be 10 squared plus 15 squared minus 2 into 10 multiplied by 15 multiplied by cos of pi over 3, just like that. And then we close. We will now multiply it by the change. So our small change in x there is just 0.1, and then we say plus. Now we do the substitution for the other term. So 2 into 15, which is y, minus 2 into 10 for x, multiplied by cos of pi over 3, all divided by 2 root of 10 squared plus 15 squared minus 2 into 10 multiplied by 50 multiplied by cos of pi over 3, just like that. And then we then close. We multiply the small change by the small change in y, which is negative 0.2. So yeah, that's it. And then you press on your calculator. Now it's just the time to use your calculator. So your small change in z for this term, this first term, is going to be root 7 over 140 minus 4 root of 7 divided by 70. So you should be able to get that partial derivative of a small change in z is going to be equivalent to negative 0.1323 centimeters. So this should be your final answer. So I hope you got it, guys. It was not that bad, right? So yeah, let's just quickly check few more questions. Is it 2 or 3 questions left, and then we'll be done for this question. Yeah, we'll be done. So yeah, let's go. So we now have what we were told that the frustum of a cone shown below is the portion of a cone that lies between two parallel planes cutting it. The volume of the frustum is given by V equals to 1 over 3 pi h r squared plus rh plus r squared, where r is the lower base radius and r is the upper base radius and h is the height of the frustum. Calculate the rate of change of V if r is changing at the rate of 0.5 centimeters per second and r is changing at the rate of -1 centimeters per second, and h is changing at -1.25 centimeters per second at the instant when r equals 35 centimeters and r equals to 22 centimeters and h equals to 42 centimeters. So we should calculate the rate of change of volume. So we're just going to manipulate the rate of change volume with the use of this equation. So let's do like always. Let's start differentiating partially with respect to r, h, and small r. So before we do that, I would like to rewrite this given equation of V in this following manner. So I'm going to multiply out there. So I'm going to multiply out. So I would like to multiply out, basically. That's what I'm trying to say. But it's the same thing, and even if I don't multiply, but okay, I'm just, let me decide, should we multiply out or should we not multiply out? Let's keep it like this. It's fine. So let's just differentiate partially from this given equation. It's fine, even if we don't differentiate, even if we don't multiply out, it's still going to give us the same thing. So now we are going to differentiate partial, so the partial derivative of V with respect to let's start with the one of caps R. So the one of caps R, so what? So that means that if we're differentiating partially with respect to R, H and small r are constants. So we're going to differentiate with this R. So we're going to get that 1 over 3 pi h into what? Into 2r plus just small r, right? Plus just small r, yeah. and then the other one would differentiate partial. So when I differentiated, this was a constant, and then I just differentiated what's inside, because this is a constant since we're differentiating with respect to r, caps r. So I differentiated that, it gave me 2r, and then this gave me just small r. And then now I differentiate again partially. So when I differentiate v again partially with respect to small r this time around, so that means 1 over 3 pi h is still a constant, and caps r is still a constant as well. So I'm going to differentiate this term and that term, because this will be 0. So this is going to just give me the constant that is outside, 1 over 3 pi h multiplied by what? Multiplied by the derivative of r squared is 0. Derivative of r is going to give us as caps r plus 2r, just like that, plus 2 small r. And then we again go further and differentiate partially again with respect to h this time around. So when we differentiate with respect to h, that means everything else is a constant, and then 1 over 3 also, 1 over 3 pi is also a constant. That means we're going to just get 1 over 3 pi, 1 over 3 pi multiplied by everything that's inside the bracket, which is r squared plus rr plus r squared, just like this. So from here, we were told that the rate at which caps r is changing is equals to what? So it's increasing at a rate of 0.5. The rate at which r changes with respect to time is equivalent to 0.5. And then what? The rate at which small r changes with time, we were told that it is equivalent to -1, as well as the rate at which height changes with time. We were told that it is equivalent to -1.25. So from here, we're just gonna rewrite the formula of the rate of change of v. So let's write down the rate of change of v in formula form. So this should be equals to the rate of change of volume with respect to time is equivalent to the partial derivative of v with respect to caps r multiplied by the rate at which r changes with time, plus the partial derivative of v with respect to r multiplied by the rate at which r changes with time, plus the partial derivative of v with respect to height multiplied by the rate at which height changes with time. Then from here, we are just going to substitute. So from here, we're just going to substitute. That means that the partial derivative, the rate at which volume changes with time is then going to be equivalent to, so I'm just going to substitute all the formulas that we have. So let me reveal them there so that you can see. So now I'm going to substitute. So here are my formulas. I'm just going to substitute them. So let's start with this one. This is going to be what? This is going to, I'm just copying. So this is going to be 1 over 3 pi h multiplied by 2 caps r plus small r, and then I close there, and then I multiplied by the rate at which caps r changes with time, plus I put the other one there. So I'm going to substitute the other one there, which is going to be the 1 over 3 multiplied by pi h multiplied by r plus 2 r, like that, and then I close, I multiply by the rate at which r changes with time, plus the last one, which is going to be 1 over 3 pi into r squared plus rr plus r squared, just like this. And then from here, we are going to substitute our values this time around. So we were told that h equals to 42, r equals to 22, r equals to 35. So we are just going to substitute there. So let's substitute now. So the rate at which volume changes with time is then going to be equivalent to 1 over 3 pi our h that we were told that it is equivalent to 42 multiplied by 2 into, we were also told that our caps r is equivalent to what? We were told that our caps r is equivalent to 35 plus small r, which is equivalent to 22. So this is equivalent to 22. Then we are going to close here and then close for the bigger bracket, and then the r the t is 0.05 0.05, and then now we can add for the other term, which is going to be 1 over 3 pi. Our height is what? It's 42, right? Our height is just 42 multiplied by our r, which is 35 plus 2 into 22 for small r, and then we close. We also close again. The rate at which small r changes with time, they said it's equivalent to -1, and then we say plus. Now we do for the last term, which is just going to be 1 over 3 pi. R squared is what? It's 35, right? So this is going to be 35 squared plus 35 multiplied by 22 plus 22 squared, and then we multiply it by, okay, here we should multiply by the rate at which h changes with time. So the rate at which h changes with time, they say it's -1.25. So it's -1.25, just like that. So just like that. So now we can find our rate at which volume changes with time. So when you press each term on your calculator, when you press this, you should be able to get something like 644 pi, and then for this term, which is multiplied by -1, is going to be 1106 pi, and then for the last term, which is multiplied by -1.25, is going to be 12395 pi divided by 12, and then therefore the rate of volume at the rate at which volume changes with time is going to be equivalent to 4696,4192 cubic centimeters per second. So this is going to be the rate at which that one changes with time. So yeah, that's it for that question. Let's quickly check another question. I think this one is a bit trickier. So yeah, we are given that the road is perpendicular to the train track. Suppose a car approaches the intersection of the road and the train track at 24 kilometers per hour, while a train is approaching at 120 kilometers per hour. At what rate is the distance s between the car and the train changing when the car is 1 kilometers and the train is 3 kilometers from the intersection? So they gave us this diagram as well to try and explain what is going on with the statement that they gave us. So let me just analyze this with you because it's a bit tricky. So here they're saying that a car and the train the car approaches the intersection of the road and the train at 24. So it means that there is a car and a train which are perpendicular. The roads of them are perpendicular to each other. So the road is perpendicular to the train track. That means that the road of the car is perpendicular to I can say the train track. So we can regard X as our train track and the road of the car as our our y here. So that means this is where the car is. So this means this is where the car is on this other side, and this is where our train track is. Okay, so what else did they say? That they say that at what rate is the distance s between the car and the train changing when 1 kilometer of the car and the train is 3 kilometers from the intersection. So the intersection is this one. So they're saying that the car is 1 kilometers away from the intersection. So that means y equals to 1 and x equals to 3. So, and then this is the distance. So s is the distance between the car and the train. So this is the car. The s is the distance between the car and the train. So yeah, that's what the question is trying to say. So we're also given the rate at which the train changes with time, and the way we're also given the rate at which the car changes with time, and the rate at which the train changes with time. So let's go. So you can see that from this sketch, to solve for s, we can use Pythagoras because of we're given this triangle, this right angle triangle. So, and we know that if we were to solve for s using Pythagoras, then that would mean that s squared, that would mean that s squared is equivalent to what? Is equivalent to y squared plus x squared, just like that. And then if we solve for x here, we'll get that s is equivalent to the square root of y squared plus x squared. Then, so this question is a rate of change question. So that means we should solve it like a rate of change question, because they said what is the rate of the distance of s. So that means we should calculate the rate at which s changes with time. So now let's start by first differentiating partial like we used to do on the other question. So partial derivative of s with respect to x first is going to be equivalent to what? So because of what differentiating a root, the square root of y squared plus x squared, we are going to put a fraction like always and say on our denominator we have 2 root of what's inside the root here. It's x squared plus y squared there. And then on our numerator, we differentiate what is inside the root. So when we differentiate what's inside the root partially with respect to x, that means we're only going to get 2x, right? We're only going to get 2x. And then we differentiate again partially with respect to y. So when we differentiate s again, when we differentiate s partially with respect to y, we're still gonna get the same thing. So this time around it's gonna be 2y divided by, so it's gonna be 2y divided by 2 root of y squared plus x squared. So you can see that the 2 and 2 are going to chop each other. So allow me to cancel them right away. So they are gone. So we were told that the rate at which x changes with time. Remember, x is the train. The rate at which the train changes with time, we were told that it's going to be equivalent to 120, right? Because this say that the train track of 24 while a train is approaching at that 120. So for the train it's 120. So this is going to be 120, and then the rate at which y changes with time, so that's for the car. So for the car is going to be 24. So suppose the car approaches the intersection of the road and the train at 24. So 24 is the one for the car, which is y. So that means here we're gonna write 24. So now we can write the formula for the rate of change of distance s. So the s, so that means the s dt is going to be equivalent to partial derivative of s with respect to x plus multiplied by the rate at which x changes with time plus the partial derivative of s with respect to y multiplied by the rate at which y changes with time. So from here we can then substitute our equations there before the values. So that means on this step we're just gonna substitute. So I'm gonna substitute x divided by square root of y squared plus x squared multiplied by the rate at which x changes with time, plus we are here we're going to substitute the other one, y divided by the square root of y squared plus x squared multiplied by the rate at which y changes with time. And then from here, so the rate at which the distance s changes with time. So from on this step now we can now substitute our values, because we have already discussed that x equals to 3 and y equals to 1. So and then the values of the rates are there, so we're just going to substitute. So we said x equals to 3, right? So x equals to 3, so this is going to be 3 divided by 1 squared plus 3 squared multiplied by the rate at which x changes with time. We said it's 120. We said this is 120 plus our y. We agreed that y equals to 1 divided by the square root of 1 squared plus 3 squared multiplied by the rate at which y changes with time is going to be equivalent to 24. And then the rate at which s changes with time, so you're just gonna press everything when you calculate. You should be able to get something like 121,43 kilometers per an hour. So you should be able to get that. So that we have successfully answered the question that was asking her to calculate the rate at which the distance is whatever. So yeah, that's it for that question. And then let's do one more question, which is gonna be the last question for this video. So let's do one question and then we close. Yeah, it was a long session, but yeah, it was worth it, you know. It was worth it. To pass sometimes requires a lot of effort. So yeah, they said consider a rectangular block of wood as shown in the diagram below. The dimensions of this block were found to be x equals to 10 centimeters, y equals to 12 centimeters, z equals to 20 centimeters. Each of these measurements were found to have a possible error of plus minus 0.05 centimeters. Calculate the maximum percentage error in the calculation of the surface area S of the block, given that the surface area is given by S2 into xy plus yz plus xz. So we're also given the diagram there. So yeah, let's go. So z equals to 120, z equals to 120, x equals to 10, x equals to 10, and y equals to 12. All right, so when we analyze this question, they want the maximum percentage change in percentage error. They want the maximum percentage error, of the surface area there. But when we analyze this question, it seems like it basically is the one of small change, right? We're not given things in percentage here, so we are going to calculate first the small change in what in the surface area, and then do the percentage change that they want after the maximum percentage error. So since also they say that the maximum percentage error, that means we should take the positives, we should take the sign that makes our small change to be positive, so that we can get the maximum percentage error there that they want. So let's go. I'll show you what is really happening there. So we are okay, I can start. Let me just rewrite the equation that they gave us there in here. So s equals to 2 into xy plus yz plus xz plus xz, just like that, plus xz. So we are going to differentiate this surface area partially with respect to these three variables respectively. So let's start. So since we are the goal, I've already told you that we need to calculate the small change first, and then then we're gonna calculate this maximum the maximum percentage error that they want. So let's go. So partial derivative of s with respect to x, how much is it going to be? So with respect to x, we're going to get 2 multiplied by y, yz, right? Y plus z. That's what I'm trying to say. And then we differentiate again partially. So the partial derivative of s with respect to y this time around is going to be 2 multiplied by x plus z. So it's going to be x plus z. All right. And then now we differentiate partially again for the last time. Differentiate partially with respect to z. This is going to be equivalent to 2 into y plus x, y plus x, just like that. So this is going to be 2 into y plus x when we differentiate with respect to z. This is going to be 0 and then y plus x. So yeah, that's it. That's correct. So now we can also write down our small changes. So small change in x, they say this is equivalent to 0. So that's going to be plus minus 0, 0.05, 0.05. And then the small change in y as well is equivalent to plus minus 0.05, and then small change in z is equivalent to 0.05. So plus minus 0.05. They said it's the same. That's what the question said. They said each of these measurements were found to have a possible error of that. So that's the small change in everything. So now we can write down our small change in that thing. So small change in the surface area. So we can write down the formula that the small change in surface area is going to be equivalent to the partial derivative of s with respect to x multiplied by the small change in x plus the partial derivative of s with respect to y multiplied by the small change in y plus the partial derivative of s with of s, yes, of s with respect to z multiplied by the small change in z. Then we just substitute everything to get our answer. So let's first substitute our formula. So the formula here, it's what? It's 2 into y plus z, and then we close, we multiply it by our small change, plus we substitute the formula here is going to be 2 into x plus z, and then we close, we multiply by the small change in y plus this one, which is going to be 2 into y plus x multiplied by the small change in z. So our small change in z is just going to be that. So our small change in s is going to be equivalent to what? To 2 into, we were told that y equals to 12, 10 equals to x, and z equals to 20. So we're just going to substitute all of the values here as well as the small changes, and then so that we can get the total maximum change in area. So because of this question said maximum, we are going to take the sign for positive. So positives, because of we must make sure that the multiplication of this term and that term is positive, multiplication of that and that is positive, multiplication of that and that are positive, so that we end up getting the maximum value. Otherwise, if we have the ones that are positive, some negative, we'll end up not getting the maximum one. So they're interested in the maximum one. We have to make sure that we get a positive value for this multiplication, positive value for this, positive value for that. So yeah, let's go. So our y is equivalent to 12 plus, I'm just substituting all of those values there. multiplied by so multiplied by the small change, which is 0,05. I'm going to take it as positive, and then 2 into my x was 10. They said it's 10 plus 20 for z, right? And then we multiply it by the small change, which is 0,05 plus 2 into our y. They said it's what? They said our y is 12, so it's going to be 12 plus 10 for x. And then yeah, that's it. Multiply by the small change, so small change is going to be 0,05. And then we use our calculator. Of course, when you use your calculator, then you'll end up getting that the small change in s is going to be equivalent to 8,4 square centimeters, just like that. So we haven't answered our question. The question said calculate the maximum percentage error. So meaning that we should first calculate, let's calculate the total surface area, because we just calculated the small change in the surface area. Now let's calculate the total surface area, and then we will divide it by that thing. We'll then divide the small change by the total surface area. So our total surface area, which is s, so s equals to 2 into xy plus yz plus xz. So our total surface area is then going to be equivalent to 2 into what? 2 into 10 multiplied by 12 plus our y, which is 12 multiplied by 20 plus 10 multiplied by 20. Yeah, then we close the bracket. We get that our total surface area is going to be 1,120 square centimeters. Therefore, now we can answer our question. Our question that wanted our maximum percentage error to be equals to the small change in s divided by s, which is the total surface area, multiplied by 100%. Therefore, now we can just substitute 8.4 divided by 1120. 8,4 multiplied by 1 divided by 1120 multiplied by 100. So divided by 1120 multiplied by 100%, we should be able to get that is 0,75%. So that's going to be your final answer for this question. So that's what they wanted. So yeah, that was it for that question, guys. And we were wrapping up differentiation. So on my next video, I'm going to start integration. So that was it for differentiation. We are done now with differentiation. I hope you really understood everything, and you're going to chop everything in your exams as well as semester tests. So yeah, that's it. I'll catch you in the next video. Take care.